All right, so we're thinking about interference here, and we now know that a key thing to look at is relative phase. So to do that, I have drawn two different waves again, but this time, instead of drawing snapshot graphs, I'm drawing history graphs. So I've chosen to look at a particular location in space, which I've called xi, and then I'm graphing how each of the two waves is changing in time. All right, so this is me sitting at a point watching maybe some waves on a string and how the string moves as a function of time, or if I thought about these as water waves, how is the water going up and down at one given location. And again, I'm trying to think about how they're going to interfere with each other given this relative phase. Now there's one obvious way that I could get a relative phase between the two waves at any location. And that is that somewhere, maybe off in the distance, the waves are being generated, and maybe they're just being generated with a relative phase, right? When I make a wave, I can imagine making it by moving my hand up and down or bobbing a leaf on top of a water surface. And however I'm making those waves, I don't have to make them together because here I'm making two waves, right? So I could make them so that my hands are going up and down with the same frequency and that they're in phase with each other. But I could just as easily make them be going out of phase with each other. Or I could even make them be going slightly out of phase. So maybe this one starts going up and down and then this one starts going up and down a little bit later, but not quite out of phase. I can do anything I want. So this delta phi could have a component that is entirely due to the phase difference, the natural phase difference between the waves. So the first question you always want to ask yourself when you're thinking about interference is there a natural phase difference that goes in here? This is actually relatively uncommon because we're typically going to deal with wave sources that are entirely in phase, so they're going up and down like this at their source together. And then occasionally you might have examples where they're exactly out of phase, but it's pretty uncommon to have any other example of an initial phase difference like this. Most of the possible difference that you can get in the relative phase actually comes from the fact that you might be different distances away from the two waves. And because you have to pick a common coordinate system when you're writing down the two waves, the difference in distance that the two waves travel might also impact the relative phase. And so what you need to do is you need to go look and say, oh, maybe I'm standing 12 meters from wave 1, but 13 meters from wave number 2. I would need to go look at the geometry of the situation and figure out the exact difference in the distances that the two waves travel. That calculation gives you something called the path length difference, which will usually use the symbol delta capital D to represent the path length difference, to indicate that it is a distance. And you can always turn that path length difference into an equivalent phase difference for the relative phase by taking the path length difference and dividing it by the wavelength, which will give you a measurement in radians instead of in meters or centimeters or whatever it is you're measuring delta D in. Once you know whether or not there's a phase difference and the path length difference, you can put those things together to figure out the relative phase, which will then in turn let you figure out what sort of interference you have. Now, as we already saw, if you have waves that look like this, that's going to be a relative phase of pi, although because of the way that circles work, it could be 3 pi or 5 pi or negative pi, right? And all of those are going to lead to destructive, complete destructive interference. So that's like the picture that we've drawn here. On the other hand, you could have a total relative phase which is equal to 0, or again, because of the way circles work, 2 pi, or 4 pi, or negative 2 pi, right? Any multiple of 2 pi will work there. And this is going to give you constructive, maximum constructive interference. On the other hand, if your phase difference is anything else, pi over 2, pi over 3, pi over 6, 3 pi over 8, anything that's not one of these, will give you something in between. Maybe it'll be a little bit constructive, but not entirely lined up. Maybe it'll be mostly destructive, but things will be shifted by a little bit. So it's not completely gone when you add the two waves together. But the key for all of it is to figure out this relative phase by looking at the phase difference and the path length difference.